Okay, so here we go. So last time we were talking about gravitational fields. We didn't get very far into this bit, but we kind of barely started talking about this. Reminder, the big idea is that this vector field representing gravitational fields structurally looks just like this vector field back here, describing how little particles, happen to be called photons, little particles shoot out of a light bulb as it happens. But the point is a flow of particles emanating out of a point source is exactly the same structurally as this vector field right here representing gravity. So with that in mind, a reasonable sort of physics-y kind of hack would be to say, let's pretend that this vector field representing forces is actually literally representing little particles called gravitons that communicate gravitational force. And so again, everything fits, because if I pretend gravity is made by particles shooting out of a point source, I get the exact correct structure for the vector field. So as I've done on several cases in the course, when something behaves a certain way, you can pretend that it actually is that, and it's not going to ever lead you in the wrong direction because, by assumption, it behaves exactly like that thing. So this is actually not something I made up. This idea that gravitons, little tiny little particles, are just constantly shooting out of every particle of mass, and that is how gravitational forces get communicated. It's I don't know if I'd call it a theory exactly, but it's an entertained thought in physics. And a very convenient crutch for our purposes. So I'm going to use it as such, independent of whether it's true. I don't really care if it's true. Right? So here's the big idea then. Let's suppose we're interested in computing so there's a bunch of stuff that we're going to be looking at in this little foursome of equations, and I'm going to walk through these equations sort of like this, in this direction, and some really nice conclusions are going to come out of this. So first is looking at this equation right here. Looks kind of intimidating. What you quickly notice is that there is a shared constant on both sides, and other than that shared constant, all this equation says is mass is a triple integral of density with respect to volume. It's of course old news. Right? One of our very first observations about how to use integrals. Right? And then the constant on both sides is, of course, perfectly legal. It's a little mysterious why we'd want to put it there. It's perfectly legal. Okay, so there's that top equation. What's going on with this equation? This is this is where I'm going to lean heavily on this graviton metaphor. So if I have a piece of mass, and if mass shoots out little gravitons in the same way that light bulbs shoot out photons, and if I ask the question, okay, all these gravitons being shot out here, how many of them will actually count as flux through this surface? All of them. Okay? It doesn't really matter even what the shape of this surface is. Every particle that originates inside the surface will eventually find its way outside of the surface. Right? So, if you had twice as many particles, you'd have twice as many particles shooting out, 100% of which would go through the surface, and therefore you'd have twice as much flux. So the big idea of this equation here, this just says that flux is proportional to mass. Which, again, in my metaphor, is just kind of like saying, more light bulbs makes more flux of light. Which, again, of course. So a pretty believable result there. Now all I have to do is write down the divergence theorem. And we are set up now to compare two triple integrals, right? These two triple integrals, we've agreed that this is equal to that, and that's equal to that, and that's equal to that. So these two triple integrals are equal to each other on the same domain. This works for any domain. Therefore, the integrands are equal to each other. And so we have actually effectively performed a tremendously difficult computation by just kind of making a couple clever observations. So in particular, we have taken this complicated vector field, which, by the way, of itself only describes what gravity looks like if you have a single point source of mass. What if you had a bunch of them? The vector field would get tremendously complicated. This, as it is complicated because it has square roots in it. Right? This is a very ugly vector field. But again, way worse if you have lots of particles of mass. And we have just successfully computed the divergence of that extremely complicated vector field. With barely lifting a finger, and what we find is that there's a very simple and convenient solution, and that is proportional to mass density. So, wonderful little result. Nice way of thinking about gravitational fields and the resulting flux and divergence. Yeah.
Where does the constant come from?
It's empirical. Yeah, I mean, so one way you could say it is it comes from units. So, in other words, mass. I don't know, are we talking kilograms? Are we talking grams? Are we talking English slugs? Right? There's various different units, and the constant depends on the units. Right? This G is what they call a universal constant, right? And so anyway, yeah, it's all empirical. Yeah. Yes.
Could you just explain one more time why that is equal to flux?
Yeah. So the idea is that mass shoots out gravitons, right? More mass shoots out more gravitons. And since any mass that's on the inside of your surface has to eventually leave the surface, then the more mass you have, the more gravitons you have. That means the more graviton flux you have, and so the total flux is proportional to the total mass. Yeah, that's the idea. Is that cool?
Yeah. Thank you.
Yeah. Okay, now, why do we talk about gravity? A lot of people make the observation that unless you're planning to be an astronaut or something like that, the gravitational field's actually pretty simple where most people live. It's constant, straight down, not that complicated, right? Do we really need big tools like this to understand gravity for most of our purposes? Arguably, no. Here's the interesting thing. Electric fields, which are not simple in the experience of most people, right? Electric fields are inside of every piece of electronics that you're working on, that you work with or on, or that you play games with or what have you. Electric fields are extremely complicated, and using complicated electric fields is a huge part of engineering, right? And the wonderful fact is that electric fields are structurally just like gravitational fields. So if you have a question about electric fields, I'm going to tell you what I always did when I was a physics major. Any question that I ever encountered concerning electric charge and electric fields, in my mind, I find electric charge to be kind of semi-unrelatable. Electric fields are this mysterious thing that people didn't even know about until a couple hundred years ago. Very hard to relate to stuff. I always just think, okay, well, charge is kind of like mass. Electric field, kind of like gravity, right? So all of these ideas here about mass and gravity give you an intuitively relatable model for understanding electric fields. And now I've got all the same equations written down here, and it's the same argument kind of going around the loop. The only difference is that now instead of mass, it's charge. Instead of mass density over here, it's charge density over here. It is now not gravitons that are shooting out of mass. Now it's some other little particle shooting out of charge that creates a flux. And by the way, there's temptation because it's electric field. It's a temptation to call those particles electrons, but that's already a thing, right? So you can't use that word, right? Anyway, the little fictional, potentially fictional little graviton-like little particles, physicists call them photons. It's a different kind of photon than what we see with.
So what would be the electric equivalent?
Yeah, that's the thing.
Have
photons.
They call it photons?
They call them photons. Yeah. And I am hazy on the actual physics involved in this, but what's very clear, you cannot call them electrons. Right? Yeah. Anyway, and what they're called doesn't really matter. It's just a metaphor, right, for what we're observing with an inverse square radial field. So anyway, you make all the same arguments that we did over there, and what you find is that this empirical fact allows you to conclude this resulting fact. And because of the fact that it's the divergence theorem that connects these two, right? First of all, this is a very strong argument for why the divergence theorem is really important in understanding electricity and magnetism. Right? It is the connection between these two different statements. And also, worth observing, these are both called Maxwell's equation. Right? Now, there's 4 Maxwell's equations. Both of these are just 2 different forms of what is commonly known as the first Maxwell's equation. This is making a statement about how charge and flux relate. This, in blue, is making a statement about how charge density and flux density relate. So, excuse me, they're really closely connected to each other. Also, a really nice argument for why it's as elegant and convenient to think of divergence as a density. Because, again, this is, no doubt, charge density. Rolls off the tongue very nicely then if you say it relates to this as flux density. Okay. All right, a little bit of physics there. Oh, excuse me. Oh, my gosh. Okay, so that's our first cut at Gauss's divergence theorem. We are going to make some use of it a little bit down the road, but for the moment we're going to move on now to Stokes' curl theorem. It's another big theorem. It's a lot like all the other theorems we've talked about. The structure is practically the same. I'm going to go through the argument one step at a time, but notice we have to talk about boundaries and what orientations mean. I have to identify what is the relevant accumulating quantity, persuade you that it accumulates. We have to make the corresponding observations about how, therefore, this is a kind of a stuff, and you can view it anyway as being a kind of a stuff, and therefore there's a density, and therefore there's a theorem. It's morally identical to several previous arguments we've made. Okay, so one step at a time, though. Let's start with boundaries. So here is a surface. Notice this is an oriented surface. Oriented meaning that it comes with a normal vector describing what we mean by the positive direction through the surface. When you have an oriented surface, you can talk about its boundary. Of course, the boundary is going to be a curve. It's kind of the edge, if you will, of the surface. But since it was an oriented surface, we're going to need to talk about what it means. What is the resulting orientation on the boundary? And again, just like every other such situation we've seen, what I'm about to show you is arbitrary. It could have been a coin flip when this was first conceived of, but the coin got flipped. And the decision got made, and the convention got set, and now with 150 years behind us, we have to stick with it. So this is arbitrary, but standard and not optional. You have to make the following choice. And it goes like this. Here's how you decide on the orientation. You look at the normal vector for the surface, right? You put the thumb of your right hand in the direction of the normal vector. Got to be your right hand. Sorry about that, but it is the sticky point. Thumb of your right hand. Now your fingers want to bend. They kind of want to curl around your thumb in a particular way. You look at how your thumb, how your fingers kind of curl around your thumb. That defines what I'm going to call a swirl. And I like to draw the swirl kind of like that. Let's see here. Let me get rid of all this green. It's kind of messing up my picture here. There we go. Fingers of your right hand define a swirl. That swirl, when you drag it near to the boundary curve, that swirl side swipes up against the boundary curve in a direction, and that direction is the direction of the tangent vector. That's the direction of the orientation on the boundary curve. Again, it's an arbitrary choice. Why the right hand, not the left hand? Arbitrary. But this is the standard. How are we doing? Is everybody? Yeah.
So is there like a convention about it having to be like an upward normal? It's just not
at all. The whole point is that oriented surfaces, there is no magic correct way to orient a surface, right? Any given surface could be oriented one way or the other. Okay. And so the point is, though, if somebody asks you, hey, what's the oriented boundary of a given surface? They have to tell you what orientation they want on the given surface. Otherwise, I don't know what you're talking about. I cannot give you an oriented boundary until you give me an oriented surface. Yeah. So the asker picks the orientation on the surface, and then you follow this rule to get the orientation on that. Yeah. Right. Okay. That's the rule. Accumulating quantity. Y'all seen morally equivalent arguments here a million times, so I'm going to go a little quickly through this, though I claim that the nice punchline is boundary circulation is the accumulating quantity. And just to be clear, boundary circulation accumulates over surfaces. Right? In other words, it is surfaces that if you cut into two and then look at the resulting pieces, that you get the accumulation. Here's the picture. I mean, you can see what I have drawn here. I have on the left, I have the orientation of S1. Notice that S1 is oriented upward. That means swirl and all that. That my boundary of S1 is oriented per the light gray picture there. And then S2 now, again, also oriented upward because it's part of the same original surface. Again, with the right hand and the fingers and the swirl and the side swipes oriented like the dark gray in the picture here. And again, as always, notice that this shared edge where I cut, where I first separated my original surface into two separate surfaces, notice that it is oriented that way as part of the boundary of S1. That same red edge is oriented this way as part of the boundary of S2. Same curve, opposite directions, cancellation. Right? We've seen it a million times at this point. How we doing? Everybody buys it? Okay. So while I'm here, I'm also going to point out, notice the flashback to Green's theorem. We're developing Green's theorem, our very first boundary theorem. The accumulating quantity was circulation. So here, different circumstance. Now we're in 3 dimensions instead of 2, but we're still looking at 2-dimensional things, now a surface and space, but a 2-dimensional thing with a 1-dimensional boundary curve over which we can talk about circulations. And circulation, again, is our accumulating quantity of interest. Okay, yeah?
So if we were asked to do something for like a cylinder, like would you need to split it up into 3 different surfaces kind of?
Well, it depends. Well, yes. If you have a weird surface that is more naturally thought of as sort of 3 surfaces glued together, then yeah, it's nice to separate them. Yeah, that's right. Yeah. All right. Okay, so again, we've been down this road a million times, so I'm going to go through this a little bit more quickly. But I claim that circulation actually happens in the interior, and furthermore, you can tell how much where. And again, it's weird and counterintuitive to think of this circulation here as happening in the interior and asking, how much of the purple circulation is happening on that green curve. They don't even touch each other. That seems like a ridiculous question, right? But that's the wrong way to think about it. The way to think about this is, and I'm going to use better colors, how much of the circulation, how much of the boundary circulation for this surface comes from boundary circulation for this little piece of the surface. And now it's pretty straightforward. If you want to know how much of the total mass was happening inside of that little piece, well, you just integrate density on that little piece. You just look and see how much mass is literally in that little piece. And I'm making the observation that this is true for any accumulating quantity. And if you want to know boundary circulation for this big piece of surface, if you want to know how much of that is happening in this little piece of surface, just compute it. We would literally compute the boundary circulation for that little green piece. That's how much of the whole is happening there. It's a local thing, in other words. Okay, so being a local thing, we can talk about its density. Again, we've been down this road several times, so moving quickly. Circulation. Again, I like to think of that as happening on the surface, not the curve. It is associated to the little piece of surface, not the curve itself. Right? The surface is the thing about which I ask, what is the boundary circulation? And then I can ask reasonably, okay, how much of that is there per unit area? And thus I get a related idea of density. So accumulating quantity per unit size, and this is what we call circulation density. So again, highly analogous to, we've made practically identical arguments in several other places. Okay. So again, here is where I skip some gory details. It's arguably important, but it's not any, it's important that it has been done. It's not important that you wade through all those details. I'm just going to skip to the punchline, and as I've done before, and here it is. There's our formula for circulation density. It's curl dot in. So you can take that as given. And again, there's a proof, and it's just not worth our precious class time. Such. Okay. Now, a weird thing I want to point to, if you look at divergence only depends on the vector field. You can look right at the formula for divergence. Right? Flux density only depends on the vector field. Likewise, Green's operator. You can just look at the formula. It depends only on the vector field. You tell me the vector field, you can compute that density. Very simple in that way. The weird thing we're noticing here is that my density depends on the vector field, but it also depends on the surface. You can see right here in the fact that you have to dot with this normal vector. The density depends on the orientation of the surface. That is weird. We did not see that with the divergence theorem, either of the divergence theorems. We didn't see it with Green's theorem. We don't see that in the fundamental theorem of calculus. Right? It's weird. It's a little uncomfortable. Not particularly happy about that right this second. Does that make sense to everybody? We'll come back and talk about that again in just a minute. I just wanted a little bit of plant a thought. What are we going to do about that? Okay. So we have all the pieces ready to be put together now, as with all our previous theorems. First, we're going to view circulation as being a quantity of interest. We're going to give it a name and a notation. We observe that circulation is an accumulating quantity. The whole is the sum of the parts. And again, if you look at what I have in blue here, it literally says the whole of the circulation is the sum, that's what integrals are, of the individual little small pieces of circulation. This is literally the whole is the sum of the parts. And then when you're talking about little parts, little pieces of circulation, that relates to pieces of area by way of course, circulation density, and again discussed on the previous page. The punchline result for circulation density here is curl dot in. And so this, what I have on the top line here, this is our first cut at Stokes' curl theorem, where we just followed the pattern of what we did previously. And notice we have circulations equaling a surface integral. Okay, yes?
So I was wondering, like, you simplify it to like dot ds, but isn't ds supposed to be like capital N vector?
No, well, so ds is two things. So this is that. That was going to be my next move, of course. But then, it's also equal to capital N ds dt, but this is if you parameterize it. This is specific to a parameterization, which we aren't doing here. Yeah, everything I have on the page, not in purple, is generic.
Okay.
Yeah, right. Intrinsic to the surface. Yeah. Okay. Alrighty. So So this NDS we notice previously seen. This is the ds vector. Now we have a kind of a surprising rephrase. Didn't really see this coming. Kind of anticipating a scalar integral here because we wanted to think of quantity per unit size. That's how we think about densities. And yet, weirdly, what we see here now, is that I can think instead of circulations as being not a scalar surface integral, but a flux integral, a vector surface integral. And that's weird. That's unexpected. Everybody happy? Okay, so this is Stokes' curl theorem. It's, like I say, it's the same ideas as we've seen in other contexts. All right, let's see an example. Here we go. This is a lot like our first examples of various previous theorems. We're going to compute a line integral where the curve is given and the vector field is given, and plug and chug. Now, the first observation I'm going to make, this is an important sort of strategic observation for when you're taking tests and stuff. Notice nowhere in the statement of the question did it tell you which of your tools to use, right? So you're going to have to decide, and you're going to have to make clever decisions. Wait a minute, should I pull back through the parameterization? It's a line integral. Maybe I should use the fundamental theorem of line integrals. Tempting, right? On the other hand, it's a line integral that immediately follows my statement of Stokes' curl theorem. Maybe we should use Stokes' curl theorem, right? So we do have several options. That's the first observation I want to make. Before we get to using Stokes' theorem on this, let me kind of just tell you why I want to use Stokes' theorem here. If we were to use a pullback, notice how ugly that would be, because this right here is my x, which means it's going to go there, and then this right here, that's my y, that's going to go there, but even worse, there. I'm going to have trig inside of an exponential, right? So, it's not that I can't deal with that. I don't know. I might not be able to deal with that. I'm not sure, but it's certainly something that I don't want to have to deal with. All right, so I don't like the fundamental theorem for this. Fundamental theorem of line integrals. That's awesome. Why don't we just use the fundamental theorem of line integrals? The bad news, keep in mind all of our big theorems have asterisks. With the fundamental theorem of line integrals, the big asterisk is you have to be able to find the antigradient. There has to exist an antigradient. Sometimes there is no antigradient. Sometimes when you play that game of trying to, get the antipartials to all line up, sometimes you can't win that game. And this is one of those times. You could try as you might, you will fail. There is no antigradient. So fundamental theorem of line integrals off the table, not an option. Now Stokes' theorem has an asterisk. And these, again, very important. And you got to be super duper careful not to accidentally use a theorem that doesn't apply. Right? That didn't make any sense. The asterisk with Stokes' theorem is this right here. Right? Just like with a couple other theorems we've seen, this only applies if you're looking at a boundary. Stokes' theorem makes no comment on line integrals on curves that are not boundaries. No comment at all. This is not a minor formality. This is intrinsic to how we even started the argument. It was critical that we were looking at boundaries so that we could have, all these cut edges, the one direction, the other, the cancellation. Being a boundary is intrinsic to the argument. So, very big asterisk. If you're going to use Stokes' theorem, your curve had better be a boundary. And then there's also the minor logistical hiccup. If it's not a boundary, then there is no surface whose boundary it is, which means there is no surface to be the domain for your new flux integral anyway. Right? So another way to say this is, again, the reason it has to be a boundary, it's not that these two integrals will be different. It's that there is no second integral. There is no flux integral to even talk about, much less for it to equal to. Okay. All right. Okie dokie. So with all that warning, let's worry now about this curve. Again, the curve for our integral, parametrized with this formula right here. Recall we've talked about parametric curves previously. You recognize this is in the xy plane because of the 0. You see the sine and the cosine, and you're like, all right, circle something, right? It's clearly some sort of a circle. It looks just like our regular unit circle, except for this minus sign. I'll point out you can view this minus sign as a reflection. It's a reflection through the x-axis within the xy plane. And so all this means is this is our regular circle, our regular unit circle in the xy plane, just reflected and thus going the other way. Is everybody happy with that? Okay. So now, the big question. Is that curve a boundary? And again, it has to be, or we're out of luck. We can't use Stokes' theorem, but this isn't a boundary, and that's that would be bad news. Good news, this is a boundary. A lot of students mistakenly think this is not a boundary because, doesn't it need to go like counterclockwise or something? Nope. That's not the convention. The convention on boundary orientations is with thumbs and swirls and stuff, right? And with that in mind, here we are. This curve is totally a boundary. It's the boundary of that disk oriented downward, because thumb in the direction of the downward normal. Look at my fingers of my right hand, swirling the correct direction, swirling the same direction that this curve is going. Yeah?
So is it just convention that like a normal circle would go counterclockwise? And that's why we know that this one...
I would make the observation that this is just as valid as if it was going the other way, the normal vector would be this one instead of that one. But neither the straight up nor the straight down is intrinsically more natural than the other.
Okay.
So it's just two different orientations. I mean, we tend to write cosine t, sine t because all else being equal, minus signs are annoying, right? But it's purely kind of aesthetics, right? So importantly, there is no natural direction for an unoriented surface to be pointing.
So
it's just you have two options.
How did you know that n would go downward?
Yeah, because I had to basically think through the two different possibilities. Let's see here. I gotta move this over. There we go. Okay, so one possibility let's see, let me do it the wrong way, just so you can see what fails. If I were to try to orient this surface upward, let's see if that would work. If I were to claim that C is the boundary of S with this normal, then okay, well, if it's the thumb in the direction of the normal, and you look at the swirl, and the swirl would go that way, and that just sideswipes in the wrong direction.
But
Does that
how
make
do we
sense?
know that this swirl is going like
Right hand,
clockwise? And
thumb, fingers, right? See how my fingers are
Yeah.
bending this way? So my fingers define this swirl.
I get that. I just
Okay.
don't get the main swirl, like
The boundary.
the boundary direction.
Oh, yeah. So that was given.
Oh, okay.
Yeah, that was. It's in the parameterization.
So that's
If I can
from
get
the
that.
negative sign.
Yeah.
So that's just what that means.
That's right. So, well, this parameterizes that curve, and my rationale for that was the argument I made about reflections and stuff. Yeah, but this curve goes that way. Yeah. Okay. So, good news, we've got a boundary. We are in business. We can totally use Stokes' theorem. And, let's see here. Here we go. Our curve, our curve, being as it is a boundary, the integral that I'm interested in is now literally a boundary circulation. Boundary circulations are fluxes of the curl through the corresponding surface. And now it's details. And I'll do those details in a second. Is everybody okay with how I got to this flux integral? Okay. All right. So, how are we going to compute this? Now, again, you have options. You have a toolbox full of tools. Take your pick. You use what's going to be the most convenient in any given circumstance, of course. Now, you could call this the ds vector, parameterize the surface. It's an easy surface to parameterize. It's clearly a graph. Z equals 0. And you could totally parameterize and compute the blah, blah, blah. As an easier trick here, always keep your eyes open for geometric good fortune. The convenient trick here is that we already know this normal vector. That normal vector, we've already agreed, is the downward unit pointing in the z direction. Like so. Also, good luck. Our curl, just a matter of plugging and chugging. By the way, make sure that you're good with this, right? Make sure that you can actually compute curl of a vector field. It's really important to be able to crank those out. Curl, in this case, ugly though this vector field was, right? The vector field's kind of nasty. The curl is 0, 0, 2. It's really nice. And so we end up with a really easy integral, you'll notice, just integral of a constant. Again, whenever you have a constant in your integrand, you can just whip that right outside of the integral. What remains is nothing more than the area. The area is a barnyard variety geometric figure, and so this integral, easy computation, minus 2 pi. Everybody good? All right. Okay, so now a couple of comments. I made this, I kind of planted this thought of discomfort with the idea that we have an orientation inside of our density. That's creepy. It's counterintuitive. It seems like the circulation density for a vector field ought to depend only on the vector field. What are we going to do about that? And do we have any, have we ever been down this road, one could ask? And in fact, we have. You may notice that in the list of accumulation theorems where I was expressing the, hey, we've never seen this before. You notice I left off the fundamental theorem of line integrals, because with fundamental theorem of line integrals, we did see exactly this. The density in the fundamental theorem of line integrals, and keeping in mind the fundamental theorem is about change as our accumulating quantity. The change density then is something that depends on f, and then dotted with our orientation. Right? So that's exactly the circumstance that we found ourselves in looking at Stokes' theorem, where our density is, okay, now, but curl, right? And again, dotted with our orientation. So we are in exactly the same situation that we were in a week or two ago, whenever that was, when we were in Chapter 6 talking about the fundamental theorem. And what we did is we observed that if you take that orientation, combine it with the ds to make a dx over here, then instead of thinking of quantity, let me do it like this. Instead of thinking of quantity as being scalar density times scalar size, we're going to instead think of it as being oriented density times oriented size. If you think about what the dx vector is, I claim it's literally oriented size. The orientation t, the size ds. That's exactly what dx is made out of. It is literally t ds. It's orientation times size. So oriented size, thus the gradient oriented density. So it seemed like a weird thing that I was doing at the time to create this strange concept of an oriented density and putting that on the gradient vector. This is exactly the idea that we need now in this circumstance. So now we find ourselves, we're no longer looking at change, but we're looking at circulation. Right? And you can think of that as scalar density times scalar size, or having combined like so, I can reinterpret this as being oriented density times oriented size. And again, that's exactly what the ds vector is. It's orientation and size. The little n is the orientation, ds is the size. So this term, oriented circulation density, I think, is a really natural way to think about curl, what curl is. And the analogy continues. Let me remind you what else we learned about the gradient vector up here. Right? So looking at our oriented change density, again, kind of a heavy-handed concept, but if you look at the two parts of it, inside of the gradient vector, there's a direction which we know is the direction of fastest increase. This is the direction the change is really happening in, right? The direction of the gradient. That's the way to go to make the change happen. That's uphill, if you will. Right? And the magnitude here. Let me color code. The U is the direction that the change is happening. The magnitude is how much of that change is happening in that direction. Is it a lot of change per unit distance? Is it a little change per unit distance? So the exact same thing happens down here. If you look at your oriented circulation density, if you break up that into its direction and its magnitude, its direction is the direction that the fluid is rotating around. It's the axis the fluid is rotating around, you might say. And the magnitude tells you how much of a rotation is happening. Is this a kind of a gentle sort of rotation, something kind of slow like this, or is it a really fast, like a tornado kind of a deal, where the fluid is rotating around really, really violently? So, nice way to think about it, right? Curl, then, in other words, curl.n is the more natural thing if you're really hooked on the idea of a scalar unit of size, scalar notion of size. But curl by itself is actually telling you more information. It's telling you how much and in what direction the fluid's rotation is happening. right? And so I document that here on the next page. So curl is telling you what is the axis that the fluid is rotating around, by what direction it points. And it's telling you, again, in some sense, and I can't quantify this, but it's telling you how fast, are we talking about a little bit of a rotation or a lot of a rotation, how much rotation around that axis there is. Everybody all right? Okay. Now, I want to address the question of how does this make sense? Can we make this mesh with intuition? Why should this dot product actually compute our circulation density? Why does the curl and the normal vector dotted help me understand how much circulation is happening per unit area? And so I have a picture that I've drawn for this that I think is very helpful. So what I have is two pictures of the same vector field. So same vector field, exact same, copy paste, not a bit different. And I'm just going to kind of walk through a couple of examples of, okay, well, let's think about how that fluid circulates around the boundary of that little piece of surface. And then we're going to think about how that fluid circulates around the boundary of that piece of surface. Let's just kind of walk through, qualitative only on this. Okay. So let's see here. So circulation. What do we expect when we're looking at a flow like that and a boundary curve like that? Intuition only. Do I feel like there's a lot of circulation happening around that boundary? And I'm going to say, yeah, actually there's a lot of circulation happening around this boundary. Watch, the vector field is always kind of going the same direction as you go around, the same direction as the curve as you go around that boundary curve. So said differently, this fluid flow is very much flowing right along the curve. Keep in mind that's what a vector line integral is. How much is the fluid flowing along the curve? Right? So whatever circulation we come up with for this little piece of area, we feel like, well, there better be a lot of circulation because, my gosh, look at it. Right? It's literally circulating right around that boundary. And so why does curl.n give us that result? Well, because look, the curl and the n are pointing in the same direction. Right? So there's, looking at what I have in blue, the flow of the fluid along the boundary, right? Those being in the same direction is geometrically simultaneous with the curl and the normal vector being in the same direction. So the significant amount of circulation that I should pick up there, yeah, I'm going to get that with this dot product. Curl.n, yeah, that's a significant dot product. They're pointing the same way. By contrast, now let's look down here at this other surface, and we've got the fluid is kind of going around like this. Again, same exact fluid, same exact vector field. Now our boundary is doing kind of like this. So, I mean, is the fluid flowing along this boundary? And it's just really not. The fluid, let's see here, let me get some specific vectors on here. Along in here, the fluid is flowing that way. This is perpendicular to the curve. It's just not flowing along the curve. We don't expect any circulation along in there. And then, okay, on the other side, at points like there and there and there, the vector field is pointing that way. Again, perpendicular to the curve. This doesn't seem like it should be. We don't feel like we should get any circulation here at all. And as it should be, notice that my curl and my normal vector perpendicular. So no circulation happening, no dot product correspondingly. Okay. All right. And then let's see here. I fear we may be out. We've got 8 seconds. I think we better bail. Okay, so we'll draw a line right here. See y'all later. Have a great weekend. We'll pick up here on Monday. Have a good one.